Usually when we talk about a medical diagnosis, there's this expectation of mechanical precision.
Right, like a binary thing.
Yeah, exactly. You break your arm, the X-ray shows that jagged white line, and the doctor just points to the fracture. It's broken or it's not broken. It's clean, it's visible, and we like that kind of categorization.
That's comforting,
It really is. But then you step into the world of education, specifically the pedagogy of learning how to code, and suddenly that X-ray machine is just broken.
Oh, completely. It's totally murky.
Right. We're looking at a landscape that is just incredibly frustrating for a lot of people. I mean, if you think back to your early computer science classes, the trauma is almost universal.
Oh man, staring at a blinking cursor for what feels like hours.
Yes.
You're just terrified to press enter because, a missing semicolon might trigger some catastrophic failure, or at least the instructor always made it sound like it would.
Totally. It's an environment built on memorizing rigid best practices before the student is even allowed to understand what a practice actually is.
Exactly, before they even get the context of software architecture.
But looking at the sources we have today for our deep dive, and we're talking about architecture blueprints, documentation, raw code exports, all for this massive 2-year passion project called the Nova School server.
It's a huge stack of documents.
It is, and it's clear someone decided to engineer a permanent antidote to that exact trauma. We have this mountain of sources from a single developer who explicitly states their central philosophy right up front.
And it's a pretty radical philosophy compared to standard IT training.
Very. They wrote that they created the server with the goal of teaching students computer science quickly, pedagogically, meaningfully, and easily.
Which is, that's the holy grail, right?
Right. And they specifically say not just rigid best practice rules. They argue that learning means actually engaging with the material, having fun experimenting, trying things out together, and discovering things.
Yeah, the emphasis on fun and discovery is so rare in back-end infrastructure design.
And the catalyst for all of this, they noted that they attended these, and they called them these cruel, rigid IT trainings years ago. And the experience was just so creatively stifling that it sparked this entire 2-year crusade to build a better system.
And the output of that crusade is, frankly, a fully realized, incredibly dense engineering marvel.
It really is.
This isn't just some lightweight web wrapper. It's a localized digital school infrastructure designed from the absolute ground up.
And the twist here is what really caught my attention. After 2 years of building what is essentially an enterprise-grade platform, instead of commercializing it, the creator noted they felt, and I'm quoting here, too old to start a company, to push this software into schools.
Yeah, that part is fascinating.
So they're just gifting it to the community.
Yeah.
Their stated goal is to prove what can actually be built to teach computer science in schools, outside of elite universities.
Right, for the everyday student.
Exactly. Without relying on massive cloud dependencies, without forcing students to buy expensive hardware, and while ensuring absolute uncompromising data security for the students.
To validate a claim like that, though, that you can teach high-level computer science across multiple paradigms securely on local hardware, that requires a serious proof of concept.
Which they provide. To prove the system works, the creator uses a highly detailed multi-language fraction calculation, or Bruchrechnen in German project, as the ultimate test. It acts as this kind of Rosetta Stone of programming paradigms.
Yeah, the fraction project is brilliant. We definitely need to dig into that.
We will. So today we're going to tear down the architecture of the server, looking at the security, the local AI integration, and the curriculum itself. Let's start with the pedagogical environment.
Okay, let's do it.
So the Nova School server bypasses the local machine almost entirely. The sources describe a browser-based workspace, a material studio for teachers to generate interactive lessons, a distributed playground for collaboration, and built-in curriculum spanning Python basics, data analysis, web front-ends, C++ NEN, and Java OOP.
The decision to move the entire workspace to the browser is a direct attack on the friction of traditional CS education.
Oh, the setup friction.
Right. If you've ever tried to set up a local development environment, you know the absolute misery of configuring path variables.
Resolving dependency conflicts.
Exactly. Matching compiler versions. Now imagine doing that for 30, 14-year-olds simultaneously on whatever random hardware they happen to own.
The environment setup phase usually consumes the first 3 weeks of a semester.
Right. So by centralizing the runtime on the server, the concept of hardware independence actually becomes a reality.
Because the server is doing the heavy lifting.
Exactly. The compilation, the execution, the memory management, it all happens on the back end. The client machine, whether it's a 10-year-old tablet or a brand new workstation, is essentially just acting as a dumb terminal.
It's just sending keystrokes over WebSockets and receiving a rendered output stream.
Yep. It democratizes the classroom instantly. You don't need a $1,000 laptop to learn C++ trim.
And the curriculum details in the sources really reflect how that stable environment accelerates the actual learning. Looking at the C++ course progression, they aren't treating the students with kid gloves just because it's a browser interface.
No, not at all.
Module 1 starts with understanding algorithms as step-by-step problem solving, but then they rapidly move into bitwise arithmetic, and it culminates in templates, pointers, and generic programming.
Which is heavy stuff.
Very. But you can't teach memory management with pointers effectively if the local environment is unstable.
Exactly. And in the data analysis module, they're having students parse CSV files and visualize data using matplotlib.
Oh.
Yeah, and the underlying system has to provision the necessary Python libraries dynamically without the student ever needing to touch pip install or worry about virtual environments.
They are teaching highly relevant modern data manipulation skills within a sandbox that just, well, it abstracts away the underlying operating system complexity until the pedagogical moment demands it.
I look at this like building a fireproof kitchen.
Okay, I like that analogy. Break that down.
Well, traditional CS education often forces students to forge the pans and source the gas line before they are allowed to cook an egg.
Right. Before you can write hello world, you need to understand the command line.
Exactly. Nova gives them a fully stocked fireproof kitchen and says, start mixing ingredients, see what happens.
But my immediate skepticism here, and I'm sure any IT administrator listening is thinking the exact same thing, is about the blast radius.
Oh, the blast radius is always the concern.
Right. If the kitchen is truly fireproof, how do we stop a classroom of mischievous teenagers from writing a script that accidentally or intentionally burns down the school's internal network?
Well, the creator explicitly prioritized absolute data security for the students, and the architectural implementation of that goal relies on heavily fortified containerization.
Okay, so Docker and stuff.
Yeah, Docker or Podman. When a student executes code, it isn't running on the server's bare metal. It's sandboxed inside an isolated container. But the hardening profile outlined in the secure.md file goes way, way beyond standard containerization.
Yeah, I was reading through that secure.md file, and they use a flag called capdropall.
Yes.
Now, from my understanding of Linux kernels, dropping capabilities strips process privileges. But what does that actually look like for the running code? Like, does that mean a student can't even ping a local host?
Let's break down what a Linux capability actually is, because it's crucial. Traditionally, the kernel operated on a binary privilege model. You were either a standard user or you were root.
Right, and root is God mode.
Exactly. Root could bypass all kernel permission checks. Capabilities split those root privileges into distinct units. So capnitra allows you to open raw sockets like a ping. capsystime allows you to change the system clock. capchichoen lets you change file ownership. By utilizing capdropall, the container runtime instructs the kernel to strip every single one of these specialized privileges from the processes running inside the container.
Wow, every single one.
Yes. Even if the student writes a script that tries to execute a binary that normally requires root permissions, the kernel simply denies the syscall. Doesn't matter what the code says.
The documentation also mentions they apply a no new privileges security option and force a read-only root file system.
Right, another massive layer of security.
So the student's code cannot modify the underlying operating system of the container itself.
Right.
If they try to delete, etc., or overwrite a system binary, it just fails at the file system level.
Furthermore, they utilize tempufs for temporary directories.
Wait, mounting directly into RAM.
Yes.
Why bypass the hard drive entirely for temp files? That seems, I don't know, resource intensive.
It's actually genius for two reasons. First, performance. When a student compiles a C++ program, the compiler generates numerous intermediate object files.
Right, all those .o files.
Exactly. Writing those to RAM, rather than a physical SSD, significantly reduces I/O bottlenecking, especially when 60 students hit compile at the exact same moment.
Okay. The disk queue would be a nightmare otherwise.
Precisely. And second, and more importantly for security, volatile memory is inherently ephemeral.
It vanishes when the power is cut?
Right. Or in this case, when the container is destroyed after the code finishes running. Those temp files cease to exist instantly. There is absolutely no residual data left on the disk for a subsequent container run to accidentally access.
That's incredibly clean.
And they mount that temps with a no exec flag.
Oh, come on, that's so strict.
Meaning, even if a student somehow downloads a malicious script into the temp folder, the kernel will refuse to execute it.
I get the Fireproof kitchen analogy now, but the resource limits look extremely tight. The server enforces a strict memory limit, usually 512 megabytes per run.
Which sounds low by modern desktop standards.
Right. If they're doing data analysis with matplotlib and parsing large CSVs, aren't they going to hit out of memory or OM errors constantly?
You'd think so, but 512 megabytes is actually quite generous for pedagogical code execution, provided the runtime is optimized. A Python process parsing a standard dataset for a high school lesson rarely exceeds 100 megabytes of RAM.
Okay, fair enough.
The tight limit is really a defensive mechanism against memory exhaustion attacks.
Like a fork bomb, but for memory.
Exactly. If a student tries to instantiate a multi-gigabyte array just to see what happens, the container's klube group hits the threshold, and the Linux out-of-memory killer instantly terminates that specific process.
And it doesn't affect the host server's stability at all.
Not a bit.
Okay, what about the network? If I'm a student, the first thing I might try is writing a Python script to scan the school's internal subnet or pull down an executable from the web.
The server defaults to turning off the reb.access permission for students entirely.
So it's just blocked at the firewall.
Better than that. When that permission is toggled off, the container is launched with network none. The container is completely dark.
Wow.
It lacks a network stack entirely. No loopback interface, no routing table, no DNS resolution. It literally cannot conceptualize the network.
So the container is dark and has no internet, and it can't traverse directories because the server explicitly blocks symbolic links and rejects any invalid relative paths with ... slashes during the workspace copy process.
Exactly.
But what about the front door? If a student figures out the admin login, the container walls don't matter. They can just log into the web interface as a teacher.
Which is exactly why the local authentication bypasses standard plaintext databases entirely. The Secure.md outlines a serious cryptographic hashing protocol. PBKDF2 to HMAC HA2256 with 200,000 iterations and individualized 16-byte salts for every single user.
200,000 iterations. That is intentionally computationally expensive.
It forces the CPU to perform the SHA-256 hash algorithm 200,000 times sequentially just to verify one single password attempt.
For a legitimate login, what does that take? A second?
Not even. A fraction of a millisecond.
Oh, great.
But if an attacker managed to exfiltrate the database and tried to run a brute force or dictionary attack offline,
The computational overhead becomes insurmountable.
right, and because of the individualized 16-byte salts, they can't use pre-computed rainbow tables.
So even a cluster of GPUs would take forever.
Exactly. And crucially, the system architecture dictates that teachers and administrators cannot see the plain text passwords of the students. The data is secured even against insider threats or careless admin practices.
Let's assume the security keeps the malicious intent out. The real threat in a classroom isn't usually a sophisticated hacker.
No, it's a bored teenager.
Right, it's a student writing an infinite while loop in Python on day 2.
Yes.
If 30 kids deploy an infinite loop simultaneously, a poorly designed system would just grind to a halt. The CPU spikes to 100%, the server hangs, and the class is effectively over for the day.
The Nova architecture mitigates this through a centralized server-side scheduler. The scheduler acts as the traffic controller for the container engine, enforcing global and role-based concurrency limits to prevent resource starvation.
The documentation gives an example for a cohort of 60 students. They say the global limit might be set to 8 concurrent container runs at any exact millisecond.
Right.
8 sounds like a huge bottleneck for 60 kids actively coding.
In human time, yeah, it sounds restrictive. But in CPU time, execution for small student projects is measured in milliseconds. The scheduler just queues the requests. But more critically, the role-based limits ensure fairness.
How does that work?
A student, by default, is allocated a concurrency limit of 1. A teacher might be allocated 2, and an admin 3.
Meaning my infinite loop.
Will only ever consume your single allocated execution slot. It might peg one core of the CPU, but the scheduler enforces a hard timeout. The default is 20 seconds for standard runs, or 300 seconds for live interactive terminal sessions.
And when that hits,
Once that clock expires, the scheduler sends a sig kill to the container. The rogue process is vaporized, your slot is freed, and the rest of the class doesn't even notice a fluctuation in system latency.
it's a remarkably resilient design, but, and this is a This raises a profound pedagogical contradiction for me.
Okay, what is it?
We have a secure, air-gapped blast chamber. The internet is completely turned off for the student's container.
Right.
If they're stuck on a syntax error and they can't query an external search engine or a developer forum, and the human teacher is busy debugging someone else's code across the room, what is the student supposed to do?
They get stuck.
Yeah. Frustration without a release valve kills the desire to learn. If they can't Google the answer, they're just going to give up.
And the creator anticipated that exact bottleneck, which leads us to the most technically ambitious feature of the entire project, the Socratic AI Mentor.
Okay, yes. The documentation details a virtual lecturer and local AI code help. Now, AI in EdTech is ubiquitous right now, but the deployment architecture here is radical because it runs entirely locally.
Yes. The sources outline a directory simply called LIT, which houses the intelligence. Let's talk about that.
The decision to run the AI 100% locally cannot be overstated in its importance. The current paradigm of educational AI involves sending a minor's chat logs, their code snippets, and potentially personally identifiable information to massive external cloud endpoints.
Endpoints managed by major tech conglomerates.
Exactly, which is a legal minefield regarding data privacy frameworks like GDPR in Europe or FERPA in the US.
Right, because you have zero guarantee that the prompt data isn't being retained to train future commercial models.
Furthermore, relying on cloud AI infrastructure mandates continuous high-bandwidth internet access, and it subjects the school district to unpredictable recurring subscription fees per student.
Which schools hate.
They absolutely hate it. The NOVA project circumvents the cloud entirely by bringing the inference engine onto the local silicon.
In that LIT directory, the server utilizes a framework called LITER-TLM, that's Late Runtime Language Model, with llama.cpp acting as a fallback.
And the recommended model specified in the docs is Gemma 3n-e4b-it-int4.liter-e-shalm. Let's unpack the technical reality of that file because that's a mouthful.
It is a mouthful. So we're talking about a 4 billion parameter model from the Gemma family, which are open weights models. The it designates it as instruction tuned, optimizing it for multi-turn dialogue rather than simple text completion.
Okay, so it can actually chat with you.
Right. But the int4 part is where the actual magic happens.
The quantization.
Yes. The integer 4 quantization is the only reason this architecture is viable on hardware a school district could actually afford.
Break that down for us. What does jumping from standard weights to 4-bit actually mean for the hardware?
So neural networks typically perform their internal calculations using 16-bit or 32-bit floating point numbers. A 4 billion parameter model in 16-bit float would require roughly 8 gigabytes of pure VRAM just to load the weights into memory, let alone the context window.
Which means you'd need expensive, dedicated GPU clusters.
Exactly. By using 4-bit quantization, the developers map those continuous floating point weights down to a discrete set of 16 possible values, represented by 4 bits.
That's a massive compression.
It drastically compresses the memory footprint of the model, allowing it to fit comfortably within standard system RAM and run inference directly on the CPU.
And this is my question, doesn't crushing the mathematical precision of the neural network from 16 bits down to 4 bits basically lobotomize the AI? How does a quantized model maintain enough coherence to debug a complex C++ pointer error?
It's a valid concern. There is a degradation in absolute theoretical reasoning, but it's largely negligible for the scope of high school or early university computer science.
Okay.
The instruction tuning of the model compensates for the loss in precision. The model has seen enough syntax patterns during its training phase that, even quantized, it can easily spot a missing semicolon, an uninitialized variable, or a logical flaw in a loop condition.
And because it's localized, the server architecture can be aggressively optimized. The documentation notes that the server loads the Gemma model directly into memory only when a student triggers a prompt.
Wait, it's not just sitting there eating RAM 24/7.
It processes the prompt, streams the tokens back to the browser via WebSockets, and if the AI remains idle for a default of 45 seconds, the server automatically unloads it from memory. It frees up those system resources for the container execution engine.
It's a really elegant resource balancing act. But the technical implementation of the AI is secondary to how it is pedagogically constrained.
Yes. I was struck by the system prompts detailed in the sources. The creator explicitly programmed rules of engagement.
This is the Socratic part.
Right. The server appends hidden instructions to the student's prompt before passing it to the Gemma model. It tells the AI, and I'm quoting here, "The AI should help you understand, not replace thinking." And never copy answers blindly, check them in your own project.
This is where the integration really shines. Because the server controls both the IDE and the AI, it can pass the hidden context to the model seamlessly.
Meaning the AI sees what the student is doing.
Exactly. When a student's code fails, the server doesn't just send the student's question. It can append the stack trace and the code state to the prompt invisibly.
But the AI is forbidden from just spitting out the corrected syntax.
Exactly the opposite of commercial coding assistants like Copilot, which are designed to maximize developer velocity by auto-completing the solution.
Because in an educational setting, auto-completing the solution destroys the learning mechanism.
Totally. The system prompts force the Gemma model to adopt a Socratic posture. It analyzes the error and responds with leading questions.
Oh, give me an example.
So instead of fixing a zero division error for the student, it will highlight the line and ask, what is the value of your denominator variable when this loop reaches its final iteration?
Making them trace the logic themselves.
Right. So we have an always available localized Socratic mentor that doesn't leak data to the cloud.
But where does this leave the human teacher? A cynical view would argue this infrastructure is designed to make the instructor completely redundant.
It's a common fear, but the documentation points to the exact opposite conclusion. The AI infrastructure is designed to elevate the teacher from a low-level syntax debugger to a high-level learning facilitator.
Okay, how?
The Nova server provides the teacher with an AI agent workflow via that Material Studio we mentioned earlier. A teacher can prompt the system to generate a complete markdown lesson plan on, say, Python dictionary comprehensions, including functional code examples and multiple choice assessments.
So it drastically reduces the administrative burden of curriculum generation.
Exactly. Furthermore, every interaction between a student and the Socratic AI is logged locally in the server's database.
Wait, the teacher can read the chats?
Yes. Teachers and administrators have dashboard access to these logs. A teacher can review the telemetry to identify systemic friction points.
Oh, I see.
If 15 students all trigger an AI prompt regarding variable scope within the same 10-minute window, the teacher immediately knows the previous lecture didn't land.
They can just pause the class and re-explain it.
Exactly. They have complete pedagogical oversight without having to physically hover over 30 different screens.
It's a very cohesive vision for digital learning. But, you know, a platform is ultimately only as effective as the curriculum it delivers.
Very true.
The creator didn't just build the server, they built a comprehensive reference project to prove the system can handle multiple programming paradigms effectively. They call it the Bruchrechnen project, the fraction calculation project.
And the fraction project is really the conceptual anchor of the entire Nova repository. It serves as a pedagogical benchmark.
At first glance, a fraction seems almost too rudimentary. I mean, why not a to-do list application or a simple physics simulation? Why fractions?
Because building a fraction from scratch exposes a student to the fundamental pillars of computer science faster and more elegantly than almost any other data structure. Well, a fraction inherently requires two discrete pieces of state data, a numerator, the Zähler, and a denominator, the Nenner. You cannot represent 3/4 as a single primitive integer.
Right, so fractions force encapsulation right out of the gate. You have to bind two distinct integers into a single, cohesive logical unit, an object.
Exactly. You must define a constructor to initialize that state. And the moment you allow user input into that constructor, you collide with edge cases.
Like zero.
Right. A student has to confront the reality of a zero denominator. This necessitates teaching error handling, throwing exceptions like a zero division error, and managing program flow when state initialization fails.
And to make the fraction mathematically functional, the student has to implement algorithms. I mean, 2/4 is computationally inefficient and mathematically imprecise, if not reduced to 1/2.
Right, the student is forced to implement a normalization routine, which requires writing a function for the greatest common divisor, the GCD or GGT.
The Euclidean algorithm.
Yes. They have to translate the Euclidean algorithm into operational code. So within this one seemingly simple mathematical concept, the curriculum demands mastery of encapsulation, object state constructors, defensive error handling, and algorithmic logic.
It's brilliant. And what makes this the Rosetta Stone of the project is that the creator implemented this exact fraction logic across Python, C++, OneScry, Java, Rust, JavaScript, and Node.js.
The code exports for all these languages are in the sources.
Yeah, and examining them side by side reveals how the Nova server facilitates learning distinct programming paradigms. The underlying mathematical logic remains identical, but the grammatical expression of that logic changes drastically based on the language's architecture.
The contrast between the Python and C++ implementations and the Java and JavaScript implementations highlights this perfectly. Python and C++ support a paradigm known as operator overloading.
Yes, I was looking at the Python export, and they use these dunder methods like add with double underscores, and in C++A they define operator plus A. The conceptual leap here is profound. Once the student defines the mathematical rules for addition within that method, they can write code that simply says F1 plus F2. The language compiler natively understands how to intercept that plus sign and route it to the custom fraction logic.
It allows a student to write code that reads like natural mathematics. The C++ export pushes this even further into modern paradigms by utilizing C++20 features, specifically the spaceship operator for comparisons.
The syntax. It visually looks like a less than, an equals, and a greater than sign consolidated into one operator.
Yeah, it's great. Prior to C++20, if a student wanted to sort an array of custom fraction objects, they would have to write separate boilerplate functions to handle greater than, less than, equality, and non-equality.
So much redundant code.
The spaceship operator performs a three-way comparison in a single expression. The student writes one concise method that cross-multiplies the numerators and denominators, returns the result of the spaceship evaluation, and the compiler automatically synthesizes all 6 relational operators.
Wow. It demonstrates that the Nova curriculum isn't teaching legacy syntax. It's teaching highly efficient contemporary software engineering.
But when you look at the Java and JavaScript exports, the grammar shifts entirely because those languages fundamentally reject custom operator overloading.
Right. If a student tries to write F1 plus F2, where F1 is an object in Java, the compiler just throws a fit.
The student has to learn explicit method invocation. The syntax becomes f1.add f2.
It introduces the concept of method chaining, where objects communicate by passing messages to one another through explicitly defined public interfaces.
Exactly, and the JavaScript implementation introduces an entirely different layer of complexity required by loosely typed languages. Coercion.
Oh yeah, the JavaScript code includes a static method called fraction.coerce. In C++ or Java, the compiler guarantees that if a method expects a fraction, it receives a fraction. JavaScript makes no such guarantees.
Not at all. A developer could pass a fraction, an integer, or a string into the add method. The coerce method teaches the student how to construct a gatekeeper.
Walk us through how that works in the code.
So the code evaluates the runtime tag of the input. If it's already a fraction object, it just passes it through. If it's a primitive integer, the code dynamically wraps it in a new fraction object with a denominator of 1. If it's an incompatible type, it throws a type error.
So the student learns defensive programming, basically protecting their logic from the absolute chaos of an untyped runtime environment.
Precisely. And then the curriculum introduces Rust.
Which is a beast.
Oh, it is. The psychological shift from the loose typing of Python to the authoritarian strictness of the Rust compiler is notoriously difficult for learners. Rust's ownership model and memory safety guarantees usually present a massive learning curve.
Yet, the fraction project breaks it down systematically. To achieve that intuitive F1 plus F2 syntax in Rust, the student must implement specific traits provided by the standard library add, sub, mul, and div.
The source code shows the student defining add fraction for an I64 integer, and conversely, add E64 for a fraction.
They are teaching the compiler exactly how to handle operations regardless of the operand order.
And look at the error handling in the Rust export. Java allows you to casually throw an exception and just hope a try-catch block intercepts it somewhere up the call stack.
Right, out of sight, out of mind.
But Rust refuses to compile if potential failure states are ignored.
When a zero-division scenario is possible, Rust forces the use of result or option enums. The student is compelled to explicitly acknowledge the failure state.
The exported code utilizes .expect-appearing, division durch null ist nicht erlaubt, forcing the program to safely panic with a defined trace rather than cascading into undefined behavior.
It rewires the student's brain to anticipate memory and logical faults at compile time rather than runtime.
And the creator didn't limit this to back-end logic either. The sources include an HTML export representing a UI labor.
Oh, right, the front-end integration.
The students take their finalized JavaScript fraction logic and integrate it with the document object model, the DOM. They build an interactive web form with input fields for the numerators and denominators and operator dropdown, and they bind their back-end calculations to front-end event listeners to visualize the math.
If you synthesize the entire Bruchrechnen curriculum, the genius is the transferability of the knowledge.
Yes.
The students are not merely memorizing Python syntax or Java boilerplate, they are internalizing universal architectural principles. State management, polymorphism, algorithmic efficiency, defensive typing, and UI integration.
Foundational paradigms that will apply to any language ecosystem they encounter in their professional careers.
And the Nova server orchestrates all of this, compiling Rust, interpreting Python, serving HTML and JS within those secure, ephemeral, TMSC-backed containers we discussed earlier.
It is an undeniably powerful vision for education.
But we have to confront the deployment reality. The creator wants to gift this to the community, bypassing the commercial startup route. But for a community gift to have actual impact, schools must be able to physically run the infrastructure.
And public school districts are not exactly renowned for their vast IT budgets or cutting-edge data centers.
Right. So how realistic is the deployment of a system this complex?
The creator addresses this head-on in the highly detailed service.md document. What is so refreshing about this project is the total absence of marketing delusion.
Yeah, they're very upfront.
They aren't pretending that you can run a highly concurrent AI-integrated digital school on some repurposed desktop sitting in a supply closet. They acknowledge that escaping cloud dependency requires investing in real local compute capability.
The hardware requirements outlined for a standard cohort of 60 to 90 students are substantial. The specifications call for a dedicated Ubuntu server equipped with 16 to 24 physical CPU cores, 64 to 128 gigabytes of ECC RAM, and fast NVMe solid-state drives configured in RAID 1.
That is a serious piece of enterprise iron.
But when you look at the aggregate workload, the specifications are entirely justified.
Oh, completely. The server is concurrently hosting a 4 billion parameter language model in memory, managing the orchestration and teardown of potentially dozens of isolated container environments per minute, acting as a web server pushing constant WebSocket traffic, and maintaining a localized database for all workspace state and telemetry.
Let's look at the specific hardware choices. Why mandate ECC RAM? I mean, error-correcting code memory is significantly more expensive and usually reserved for high-end enterprise or scientific deployments.
Well, in a standard desktop, a bit flip in RAM caused by background radiation or minor electrical interference might cause a browser tab to crash. It's an annoyance. On a centralized server hosting gigabytes of neural network weights and executing student code, a bit flip is catastrophic.
Really? How bad could it be?
A flipped bit in the Gemma model's weights could induce a severe hallucination, outputting syntactical garbage to a student asking for help. A flipped bit in the Solite database could corrupt a student's entire semester of work.
Oh, wow. Okay, yeah.
ECC memory detects and corrects these single-bit errors dynamically. For an environment where 90 students might be taking a high-stakes coding exam simultaneously, that stability is non-negotiable.
And the documentation specifies NVMe drives in a RAID 1 array. Now, RAID 1 is mirroring every piece of data is written identically to 2 separate drives.
All right, storage drives, especially those subjected to the constant read-write cycles of teampf swapping and container instantiation, will eventually fail.
It's just physics at that point.
RAID 1 ensures that if a primary NVMe drive dies mid-lecture, the operating system instantly pivots to the mirrored drive without dropping a single WebSocket connection.
And the service.md also notes the use of squile in wall mode write-ahead logging.
Yes, which is crucial for concurrency. Standard Squilite locks the entire database file during a write operation, which would cause massive bottlenecking if 60 students tried to save their files concurrently.
Wall mode bypasses that locking mechanism, allowing simultaneous readers and writers by appending changes to a log file before committing them to the main database.
The creator isn't just providing code here, they are providing highly sophisticated enterprise-grade architectural consulting for free.
This highlights the true cost of cloud independence. To escape the surveillance and recurring fees of major cloud providers, a school essentially has to build and maintain a localized microcloud.
But the financial calculus often favors this model for public institutions. Acquiring a robust server might require a one-time capital expenditure of $5,000 to $8,000.
Right.
That is often much easier to justify in an annual district budget than committing to unpredictable, recurring software as a service licensing fees that cost hundreds of dollars a month per student in perpetuity. You purchase the hardware, and the district owns the infrastructure indefinitely.
The service.md also issues strict warnings regarding production security. They explicitly instruct administrators, never expose the HTTP server directly. The traffic must be routed through a TLS terminating reverse proxy like Caddy or Nginx to ensure all communication is encrypted.
They even supply the necessary configuration syntax.
And they mandate the immediate rotation of default credentials like admin.novaschool.admin. They are handing over a highly tuned engine, but they are bolting the safety manual to the dashboard.
It demonstrates a deep, pragmatic understanding of how infrastructure actually fails in under-resourced public IT environments.
Which brings us back to the creators' justification for making this project open source. They stated they felt too old to start a company. Do you think age or fatigue is the sole reason a developer gives away 2 years of intense, highly marketable software engineering?
I doubt it.
I mean, they could have easily taken this architecture, wrapped it in a slick UI, and sought venture capital funding.
The too old comment likely masks a deeper philosophical stance on the ethos of educational technology. The reality of the tech industry is that accepting venture capital fundamentally alters the trajectory and nature of a product.
Because the investors need an exit strategy. They need a return on their capital.
Exactly. In the edtech sector, generating that requisite recurring revenue usually dictates one of 3 paths. You monetize the behavioral and performance data of the students, you gate the most effective pedagogical features, like the Socratic AI Mentor behind premium paywalls.
Or you lock the school district so deeply into a proprietary cloud ecosystem that migration becomes financially impossible.
By refusing to commercialize the Nova School server, the creator ensures that the core mission remains insulated from market pressures.
Right.
The pedagogical integrity, the absolute data security, the localized AI, and the hardware independence cannot be compromised to satisfy a quarterly earnings report because there are no earnings to report.
The gift itself is a mechanism to protect the architecture.
It is a profound rejection of the idea that high-quality educational infrastructure must inevitably become a mechanism for data extraction or vendor lock-in.
When you synthesize the entire architecture, the Nova School server is really a masterclass in building software with a deep ethical purpose. It was born from a place of frustration with the rigid, joyless IT training of the past. Over 2 years, a single developer engineered a highly secure, localized, AI-assisted platform capable of teaching everything from basic Python to memory-safe Rust without ever relying on external cloud dependencies.
And they proved its efficacy with the comprehensive Bruchrechnen curriculum.
And then they just gave the entire blueprint away to democratize access to genuine computer science.
The project challenges anyone working in technology or education to examine the tools we build and deploy, and to critically evaluate whose interests those tools are truly serving. Are they serving the learning process of the student or the revenue model of the provider?
If you've ever felt the friction of trying to learn or teach complex technical concepts in a hostile digital environment, this project proves that the friction is a choice, not an inevitability. We don't have to accept the broken X-ray machine of traditional educational infrastructure.
No, we don't.
And it leaves you with a final provocative thought to consider. If a single, passionate developer can build a secure, localized, AI-powered digital school in 2 years and simply give it away to prove what is possible, what other systemic barriers in our educational systems could we completely dismantle if we stopped trying to monetize them and just started building?